Okay, so suppose the numbers a sub n are defined recursively by, so a sub 1 is 1, a sub 2 is 2, a sub 3 is 3, and for n greater than or equal to 4, a sub n is the sum of the three preceding terms. We wish to use the principle of complete induction to show that a sub n is less than or equal to 2 to the n for every positive integer n. So proof by the principle of complete induction. Okay, so our base step, so we're going to consider, so positive integers, so p of 1. So we know a sub 1 is equal to 1, and 1 is definitely less than or equal to 2 to the 1. So that checks out. And now let's go ahead and look at consider p of 2. We have a sub 2 is equal to 2, and that's definitely less than or equal to 2 squared. That checks. Let's consider p of 3. We have a sub 3 is equal to 3, which is definitely less than or equal to 2 cubed. And now let's consider p of 4. So we can just see how the recursive formula works, right? So a sub 4 is just the sum of the three preceding terms. So that's a sub 3 plus a sub 2 plus a sub 1, which was 3 plus 2 plus 1, which is 6. And 6 is definitely less than or equal to 2 to the 4th. Okay, so it looks like this is going to be true. So induction, step, suppose p of 1, p of 2, dot, 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 p of k minus 2, p of k minus 1, and p of k are all true, right? Now let's go ahead. So this tells me that the statement is true for all the terms up to k. So this tells me that, for instance, a sub k minus 2, we're assuming that this is less than or equal to 2 to the k minus 2. We're assuming that a sub k minus 1 is less than or equal to 2 to the k minus 1. And we're also assuming that a sub k is less than or equal to 2 to the k. Now let's go ahead and consider a sub k plus 1. Well, by definition of this sequence, right, we know this is equal to a sub k plus a sub k minus 1 plus a sub k minus 2. And by our induction step, right, we know a sub k is less than or equal to 2 to the k. We know a sub k minus 1 is less than or equal to 2 to the k minus 1. And we know a sub k minus 2 is less than or equal to 2 to the k minus 2. So then, of course, their sum is less than or equal to this sum, right? Now, I know this is strictly less than, so 2 to the k plus 2 to the k minus 1 plus 2 to the k minus 1. Because 2 to the k minus 2, right, is definitely less than 2 to the k minus 1. Okay, so now this is equal to 2 to the k plus 2 times, there's 2 2 to the k minus 1s, right? So that's going to be 2 times 2 to the k minus 1, because there's 2 of them, right? Okay, well, 2 times 2 to the k minus 1 is the same thing as 2 to the k plus 2 to the k, right? Because this will be 2 to the k minus 1 plus 1, so that's just 2 to the k, right? So this is equal to, now we have 2 to the k's, right? And of course, that's the same thing as 2 to the k plus 1, all right? Okay, so we were able to show that a sub k plus 1, assuming the three previous terms were true, right? Three previous terms were less than or equal to 2 to the k minus 2, 2 to the k minus 1, and 2 to the k. We're able to show that the next term in the sequence was less than or equal to 2 to the k plus 1. So thus, a sub k plus 1 is less than or equal to 2 to the k plus 1. Therefore, by the principle of complete induction, for every n contained in the positive integers, we know a sub n is less than or equal to 2 to the n for this a sub n sequence, right? Q, E, D.